Hello, Riles. So lesson 7.7 is a little long because we have different ways of working with distances in R2 and R3. Some people don't deal with it as a separate lesson. They just have students kind of develop their own way of finding these distances as extension problems. But I really like taking the time to look at more than one way of doing the problem. So I think what I'm going to do is just sort of walk you through a couple of the theories behind the approaches. So let's start in R2 here. The first approach that I use in both 2D and 3D is trying to build a use of the scalar equation. So what I'm going to do is I'm going to have some point P1 off of the line, and this sometimes will be labeled Q in some applications. It doesn't really matter what it's labeled. The thing that I guess I need to keep track of is the fact that P1 is not on the line, or may not be on the line. If it's on the line, then my distance formula will tell me that the distance is 0. Okay. In R2, the thing you want to keep track of is the fact that you have a unique normal. Okay, or two unique normals, two unique unit normals. There's a definite direction that is perpendicular to this line, and you don't have that in R3. Now, since I have a normal, I decide to use my angle theta as the angle between the vector P1, P0 and the normal vector here, or its supplement, doesn't really matter. Right? So here's that distance, and just using a cosine ratio, the cosine of theta is this distance divided by that distance. I rearrange and I get that S is the absolute value of the magnitude of P1, P0 times the cosine of theta. Now, I could stop there, but I probably don't want to have to calculate the angle theta. So I multiply by 1 in the format of the mag of the normal divided by the mag of the normal to build a dot product. I could still just substitute into here if I want to, but if I know a Cartesian equation, I'm able to develop this a little bit further. So what I do is I substitute in expressions for the vector P0, P1, which is x1 minus x0, comma y1 minus y0, dotted with my normal, which is going to be a comma b. Here's the magnitude of my normal, square root of a squared plus b squared. I use the distributive property of the dot product. I use the distributive property of multiplication, and then I rearrange and I recognize this expression. This is where, again, I don't think it's great if you have this memorized because your reader might not have it memorized. I'm going to argue that since P0, x0, y0 is on L, it'll satisfy the equation. So that means that a times x0 plus b times y0 plus c will equal 0. In other words, this expression right here is c. So that's how I get this formula. I don't think it's worth it to bother memorizing this formula. It's not an efficient approach if you aren't given your equation in standard form, in Cartesian form. Good. Another approach that I think I did in the lesson. Sometimes I only did one version of each approach in either 2-space or 3-space. So if I'm trying to find the foot of the perpendicular, a decent option is to set the dot product of P to some, P1F dot D equal to 0. So make F some sort of variable point on there. One of the approaches I definitely showed in the lesson is finding some general point P on the line and writing the magnitude of this vector in terms of t and minimizing that magnitude using derivatives. It's maybe not the fastest way of doing things, but it's kind of neat to get a little bit of review of calculus and to see how we can combine calculus and vectors. Okay. So here's me working through some examples to find the distance from this point to that line, just substituting in works okay, developing using a scalar projection. And then in this case, I stop. I don't continue to try to develop the Cartesian equation. I just substitute into my scalar projection formula. That works okay as well, and it gives me the same value. Here is an example of the vector projection for the same question. I take some point on the line and the point off the line, and I'm going to introduce f. I should probably say let f be on the point, and I'm going to set qf to be the vector projection of qp0 onto my normal right there, which is 5, -3. If you feel comfortable with the projection formula, which I think you should. It's one of the formulas that I'm going to suggest you memorize because the development takes a while. It's something I want you to be able to do, but it takes a while. The formula itself is actually pretty simple. This dot that over that dot that times that. I substitute in my components. I have a couple of simple little dot product calculations, and then I argue that two vectors are equivalent if and only if their corresponding components are equivalent. That gets me the coordinates of the foot of the perpendicular. It's a little bit longer now to find the actual length. I would now need to use a length formula. But sometimes if you're asked to find the foot of the perpendicular, finding the length isn't a great first step. So if you have to find both, you might as well find the foot of the perpendicular first. Here is me minimizing the distance. I think I did this in the lesson. Again, introducing a general point, letting it be an element of the line, taking my derivative. I took the long way through the derivative here. It might have been easier if I had called this function the magnitude of qp squared, because I know that none of this mess contributes towards a root. I just tidied that up quickly. When I set my derivative equal to 0, I just look at this factor here and say the only way that this expression can equal to 0 is if that factor is equal to 0. It gets me the value of t that yields the foot of the perpendicular for me. And just hang on to this value of t because I stop when I reach this value of t in my other approaches. Setting qp.d equal to 0, making sure that some general vector from a point off the curve to a movable point on the line is perpendicular to a distance, or sorry, the direction vector, is a pretty fast approach for getting the parameter that tells me the foot of the perpendicular. Maybe not the fastest way to get the distance, but pretty fast way of getting the foot. And just to show you that you can use either the direction vector or the normal vector in R2, you could also set QP, your variable vector, QP equal to be a scalar multiple of n. The sort of awkward thing here is that it does introduce another unknown. So you've got your parameter t, but then you also have the unknown k. But you'll be able to solve that system and just solve for the value of t as well. In R3, the thing to keep track of here is that you have no unique normal. So this means if you're going to develop an approach, you probably want to move your angle of reference to over here. You know, if you have a normal, you should use it. You'll find the proofs a little bit easier to follow in R2 if, sorry. I think you'll find the proofs a little bit easier to follow to figure out how they've decided what to do. If the writers of the textbook or usually the author of my notes, me, has a normal, they choose to use it because it does simplify things a little bit. In this case, we don't have a normal. We have, so I'll measure the angle between this vector and the direction vector or its supplement. The sine ratio of the angle or its supplement will be the same, so I actually don't require an absolute value here this time. What I discover is that if I'm looking for side length S, I now have the opposite side length and the hypotenuse, which means I use a sine ratio, which means I'm building up to a magnitude of the cross product, not a dot product. An easy way of separating this formula from the dot product formula in R2 is that you don't have a cross product in R2. It's kind of interesting how this formula will give you the right number if you try using this formula to find a distance in R2. But students that try doing it on a test or a quiz always lose a mark because I ask them to explain what the cross product in R2 means. And no one is able to because it doesn't exist in R2. Okay. You might be able to notice that some of these other approaches actually work fine in R2 or R3. And again, I don't think I duplicated any of these approaches in our lesson, but you might want to try them out. I don't know why these points and vectors only have 3 components or coordinates. I've been using this for years. I guess it's so just sort of goes to show that it doesn't matter whether you're in R2 or R3. You can always set P1P dot D equal to 0, and that'll give you your foot of your perpendicular. You can set the projection of P1P0 onto D to be the vector FP. That's a bit of a different approach, but still a vector projection. Okay, the argument here is you want this vector projected onto your direction vector to be that vector right there. And that will give you the vector FP0. If you know the coordinates or the components, sorry, no, coordinates of P0, then you can find the coordinates of F. Okay. So let me just walk you through a couple of other examples here. Let's find the distance from this point to that line. I'm going to build my formula. So here's my sketch. Here is my scalar projection calculation, really just grade 10 right-angled trig. I don't know the angle in between the vectors, so I try to build to a formula that I recognize. I recognize the magnitude of the cross product. Okay. I substitute in, do a little bit of crossing, and there's my distance, 6. Let's see. Different approach here. Let's try setting P1P dot D equal to 0. I've got my direction vector. I've got P1, I introduce P, the general point. I really should communicate that a little bit clearer. I set that equal to 0. I get a nice linear equation. It tells me the value of the parameter that will generate my foot, that will point to my foot. So I conclude that my foot will be found at 1, 5, 2. And if that's what I was asked to find, the point on this line that is closest to there, then I'm done. If I'm asked to find the distance, then I just need to find the magnitude of a vector. So pretty straightforward. I just find a displacement vector P1F, and into that, I take that, I substitute it into my magnitude formula. Let's try the projection formula. Let's set the projection of P1, P0 onto D to be FP0. So here is the projection of P1, P0 onto D. All of that is known. FP0, I'm going to introduce the general point. This is actually more the point P. That's every single point on the line again, built from the parametric equations. And then I find a variable vector from FP0. FP0 is going to be given by these components here, 0, negative t, negative t. And it's kind of a weird situation in here that you actually get two equations that have to agree with each other, but they both tell you that t is equal to 3. That is the same value of the parameter here that points towards my foot. So you can find your foot, you can find your distance. Okay. Do your best with the homework, but sometimes the homework kind of concentrates on that Cartesian equation a little bit too much. Make sure you try more than one method. In fact, I think on the outline, I suggest using a couple of methods for at least one of the questions. And let me know how you're doing.